Just last week at Google's Cloud Next, we announced our 7th generation TPU, Ironwood. And obviously that's not dependent on 448 gig, but we have a pipeline of follow-on TPUs that are gonna have more and more capacity and super pods that can scale with more and more chips. The Ironwood can scale to up to over 9,000 TPUs in a super pod. So with that, there is high-speed I/O required between those TPUs that's really driving the amount of bandwidth we need to get out of that package. And the package limitations in terms of signal and the number of signal I/O we can get off there is what's driving the need for higher speed per signal pair. I think by 2028 is when we're expecting to have a need for 448 gig. And we need solutions to get that signaling from the package out to front panel pluggable modules so that we can support interconnects that are copper-based within a rack and optical-based to go between racks and through our optical circuit switch, and in some cases even farther if we're constrained by the building size of the data center. From a TPU, you're supporting the scale-up network as well as the scale-out network. I think you're going to need a total capacity in the orders of tens of terabits to 100 terabits per second per package. It also depends on how the evolution of the package goes, where if you're able to put multiple dies in a single package, then that's going to drive the total package capacity even higher, like some of the speeds that NVIDIA announced on their roadmap for GPUs. Today, for 100 gig I/O and 200 gig I/O, the modulation used is PAM4, so we can transmit 2 bits per symbol. And that dictates, to get a certain bit rate, what your symbol rate needs to be, which then drives the frequency component of that signal. As we go to 400 gig, if you just double the symbol rate from 200 gig and continue with the PAM4 modulation, we're now requiring over 100 gigahertz of Nyquist frequency, which is going to be quite challenging, if not impossible, to get escape, even using like a co-packaged copper type connection, but getting it out to a module. Because you not only have frequency dependent loss of that channel, but any sort of small reflections or imperfections in that signal is going to dramatically distort it. There have been a number of good talks this afternoon showing really channels falling apart beyond sort of 80 gigahertz. So if you look at a higher order modulation, which like PAM6 or PAM8, you can now transmit more bits per symbol. So your symbol rate goes down for the same effective bit capacity of that channel. And then the Nyquist frequency comes down as well. However, those higher modulations like PAM6 or PAM8 require better signal to noise ratio because you have more levels. PAM is how many levels of amplitude you have per symbol. And now in order to differentiate between more levels, you need a higher signal to noise ratio. So going beyond PAM8 is probably not feasible from a signal to noise ratio point of view. The decision about which is better between PAM6 and PAM8, I'd say the jury is still out until we have a better understanding of what's the sort of signal limitations or signal properties that we can achieve as we look at maybe improving on the module connector and signal integrity and exactly how we're getting these signals from the SerDes inside of the package out to some sort of twin-ax or similar interconnect to get out to the module. With the large language model training jobs in AI today, this requires tens of thousands, even over 100,000 TPUs or GPUs in a single cluster. And this is what's really driving, in order to efficiently handle those models, in order to efficiently handle those models, if you can get more compute into a single chip, you don't need as many chips for the same level of complexity. However, now your bandwidth coming in and out of each chip and the bandwidth between chips is going up. And that's what's really driving the need for higher speed signaling. 448 is the next logical step on that path.